If you are interested in audio, you have probably heard or read breathless accounts describing the ultimate tube or valve sound that only a single-ended triode, SET, and directly heated triode, DHT, Class A amplifiers can deliver. Vacuum tubes such as the 300B, the 2A3, 45, 211, 845, etc., reportedly can achieve a level of sonic perfection that cannot be matched by any other technology. So to satisfy my curiosity, I decided to design and build a pair of pure Class A DHT SET monoblock amplifiers based on the esteemed 300B output tube. This video documents the design and construction of a pair of single-ended Class A monophonic tube audio amplifiers, including some discussion about the design decisions that were made along the way. I built these amplifiers the traditional way. They contain no solid-state devices of any kind. They have no transistors, FETs, integrated circuits, silicon diodes, microprocessors, LEDs, or any other solid-state components. There are no printed circuit boards either. All of the wiring is point-to-point, and soldering was done by hand with lead solder. I chose AA334 for the model number because the output tube is a 300B and the driver tube is an EL34. The AA334 is not a kit. The circuit is my own design, and I built these amplifiers using hand tools. The output tubes are 300B directly heated triodes. This means that the heater filament itself is the cathode. Currently I am using a matched pair of new production Electro-Harmonix Gold Grid 300Bs that were made in Russia. Power output with the Electro-Harmonix Gold Grids is 6.5 watts RMS at 1% total harmonic distortion plus noise, 8 watts RMS maximum, and at 1 watt RMS the total harmonic distortion plus noise measures 0.24%. The AA334 amplifiers use no global or negative feedback. The amplifiers are capable of driving a pair of clipped Cornwall 2 speakers to very satisfactory levels. The Cornwall 2s are really dynamic and with a rated sensitivity of 101 dB for 1 watt at 1 meter and with low distortion. The 300B is a very linear triode, but it requires a grid signal of about 150 volts peak to peak to drive it to full output. Because of this high drive requirement, I decided to use a triode connected EL34/6CA7 as the driver tube. The EL34/6CA7 tube was designed for audio and has very musical characteristics, especially when configured as a triode. It is a power tube, so it is capable of driving the 300B with ease. I am using JJ EL34s from the Slovak Republic, but I plan to test other makes as well. The output transformers are hand-wound Silk S325F from SAC, Thailand. They are rated for up to 20 watts output power and are properly gapped for single-ended Class A use. The output stage. I used the indispensable SE AmpCAD software to design both our output and driver stages. SE AmpCAD was written by John Broski of TubeCAD Journal. John has also created many other very useful programs. The famous Aikido line stage kits are available at the TubeCAD site as well. This is the SE AmpCAD screen with our parameters. I decided to use cathode bias for the output tube because it is self-adjusting and I didn't want to have to make periodic adjustments. I left the cathode resistor unbypassed, which helps reduce distortion. The Silk S325F output transformers were not in SE AmpCAD's transformer list, so I created a new record and entered the specifications. Here are the grid curves for the 300B tube. The program plotted our load line as well as Vmax, Imax, WP, and other curves based on the parameters we entered on the left side of the screen. Beneath the curves you can see the results of the key calculations performed by the program based on our input. Having this software do all the calculations is so great. It gives us the freedom to experiment and to try as many what-if scenarios as we want. These are the calculated grid and plate traces for a 1 kHz sine wave. And this is a scope trace of a 1 kHz sine wave at the amplifier's speaker terminals. 2.83 volts is equivalent to 1 watt RMS into 8 ohms. Notice how well the actual waveform corresponds to the SE TubeCAD trace in the previous picture. The AA334 input stage. The AA334s are basic amplifiers, which means they have no volume control, tone controls, or input selectors. They are intended to be controlled remotely by a preamplifier or a receiver unit which provides the user interface for the audio system. Pictured here is an early version of the input stage on the test bench. The 6SL7 is a nice sounding tube. The even spacing between the grid voltage curves is an indication of the tube's linearity. Each tube contains 2 identical triodes in a glass envelope with an octal 8-pin base. I chose the symmetrical totem pole, or SRPP, topology primarily because of its inherently low distortion, its low output impedance, and its ability to drive our EL34 driver stage. The 2 triodes in the totem pole are DC coupled and the stage is inverting. I used TubeCAD software to determine the best operating point for our 6SL7 SRPP input stage. After entering the parameters for the circuit, I hit the calculate button and the program crunches all the numbers. As our design progressed, eventually the entire amplifier ended up laid out and working on the test bench. There was high voltage all over the place, completely exposed. You really have to keep your wits about you and one hand in your pocket. The AA334 power supply. The AA334 high voltage transformers are new old stock Canadian Armed Forces surplus Hammond 279Z. The high voltage windings are rated for 850 volts center tapped at 172 milliamps. There is a 5 volt center tapped at 3 amp winding for the rectifier filament and a 6.3 volt center tapped at 5 amps for the other tube heaters. These transformers are over spec, but they will run cool and be reliable, and I had 4 of them in stock. The Z mounting bracket supports the entire transformer above the chassis. This worked out perfectly since it gave us enough room underneath to mount the filter choke, a 5 volt transformer for the 300B heater, plus a 6 0.3 volt 4 amp bucking transformer. More on this below. I used the free PSU Designer 2 software from Duncan Amps. The analog power supply CAD program supports most popular tube and solid-state power supply topologies, and the results are quite accurate. I had a few 5U4GB rectifier tubes in stock. It has a maximum current rating of 300 milliamps. I expect the AA334 will require about 130 milliamps at 450 volts, so the 5U4 should live a long and happy life. The power supply filter is a fourth order RC, LC, RC, RC configuration. R is resistance, C is capacitance, and L is inductance. Class A amplifiers need clean power. They always draw maximum current, even when they are idling, so they are quite sensitive to ripple voltage on the B+. This power supply might seem like overkill, but the additional cost was not significant, and the result is a pair of very quiet amplifiers. This is a close-up of the power supply filter section under the chassis. C1 is a 22 microfarad 630 volt obbligato film capacitor, which is mounted above the chassis between the two transformers. The other filter caps are high-quality Nippon Chemicon electrolytics mounted underneath. Each electrolytic capacitor is bypassed by a small value film capacitor and a flame-proof metal film bleeder resistor. Bleeder resistors ensure that the filter capacitors discharge when the power is turned off. All the tube filaments are AC powered, including the 300B. A small 5-volt center tap 3 amp transformer under the chassis supplies filament power for the 300B. The center tap is connected to circuit ground through a 1000 ohm 50 watt resistor. A cathode current of 74 milliamps through this resistor results in a bias of minus 74 volts DC on the 300B grid. An increase in cathode current would increase the negative bias on the grid, which would tend to reduce the cathode current. Inversely, any decrease in cathode current would decrease the negative bias on the 300B grid, which would tend to increase the cathode current. This helps to promote long-term stability as the tubes and other related components age. The most common primary voltage rating for older transformers, and even many new ones, is between 115 and 117 volts AC. But in recent years, electrical utilities have increased the voltage at our wall outlets to between 120 and 125 volts. The higher voltage can put undue stress on power transformers and can reduce tube life by changing operating points. Our solution is a small 6.3 volt filament transformer connected counterphase with its secondary winding in series with the amplifier's AC supply. This effectively reduces the AC line voltage by 6.3 volts, which allows us to use our NOS new old stock transformers, delay relays, and other components at their proper design voltages. Each AA334 monoblock draws about 100 watts from the power line. Let's see, 100 watts in and 6.5 watts out. That's not terribly efficient no matter how you look at it. But we did specify pure Class A, didn't we? AA334 chassis preparation. I started with a pair of blank Hammond 1444-24 chassis and bottom panels. Each chassis measures 8 by 12 by 3 inches and is aluminum with a natural finish. I created matching templates in Corel Draw for the front, top, back, and bottom panels. The templates are drawn to scale and act as guides for drilling and punching. The templates were printed on removable label stock and applied directly to the chassis panels. I positioned the power transformer and output transformer near the back of the chassis. The large filter capacitor and the 6NO45 amperite delay relay sit between the transformers. All the tubes are at the front. Looking at the chassis from the front, the 6SL7 preamp tube is on the left, with the EL34 driver tube next to it. The third tube is the 300B output tube, and the fourth tube is the 5U4GB rectifier. This layout keeps the preamp tube as far away as possible from the rectifier and power transformer. Although the output transformer is relatively close to the 6SL7, the transformer is well shielded and scope tests found no trace of any feedback issues. This is what the chassis looked like with templates applied. After marking the center of every hole with a center punch, I proceeded to drill, punch, and file as required. And this is where our hands get dirty. The templates help protect the surface of the chassis during the various machining operations. I don't have any fancy CNC machinery yet, just a drill press and some basic hand tools, so this is not my favorite part of the project. Most of the holes are round, so I drilled them or punched them using Greenlee chassis punches of various sizes, but the rectangular hole for the IEC powered cord connector on the back panel had to be made the hard way. Drill and file. Every hole had to be deburred by hand, inside and out. After drilling, punching, and deburring, I peeled the templates off and then wet sanded the two chassis. Next was degrease, primer, and up to 4 coats of black textured lacquer. Pictured here are the two chassis ready for primer. The back panel labels were prepared in Corel Draw and then printed and laminated. The labels are held in place by the switches and binding posts. The speaker terminals are on 3/4 inch centers to accommodate standard dual banana plugs commonly used for speaker connections. The tube sockets are next. I used ceramic sockets with gold-plated pins for all of the tubes. The 4-pin sockets for the 300B output tubes are shock-mounted with rubber O-rings. 300Bs can be somewhat microphonic. The 50-watt aluminum resistor is mounted on the inside of the chassis and uses it for a heat sink. I mounted a 2-inch by 6-inch piece of 0.06-inch thick scrap aluminum between the resistor and the chassis to spread the heat and prevent a hot spot. It works well. The entire side of the amp becomes only slightly warm after extended use. Connects the cathode of the 300B tube to circuit ground and generates the 74-volt negative bias for the grid. Next, I mounted some of the major components inside the chassis. I should have installed the large obbligato filter capacitor before I mounted the power switch, since the capacitor has to be inserted from the underside of the chassis. Duh. Hey, after 40 years it takes a while to get back up to speed. The amplifier's circuit ground is isolated from the chassis to prevent ground loops, which can cause hum. The audio system's circuit ground will be connected to the power line ground at only one point, most likely at the preamp. The 1.5 amp circuit breaker on the back panel is a necessary safety feature. A fuse would do just as well, but I had these in stock. Now we are ready to mount some serious iron. There, that looks better. The old sock I put on the big filter cap is there to prevent scratching the fresh paint. Class A amplifiers are sensitive to power supply ripple. The AA334's beefy supply provides ripple-free power under full load conditions due to its multiple filter stages and energy storage capabilities. The electrolytic filter capacitors are mounted inside the chassis. The main leg of the ground bus is visible above the tube sockets. The power transformer's Z mounting bracket raises the entire transformer above the chassis. This leaves room to mount the smaller filament and bucking transformers directly underneath it, under the chassis. The third Hammond inductor, mounted at 90 degrees to the other two, is the filter choke. All of the resistors except the big wire wound are 2-watt metal film. Metal film resistors are stable and are low noise. Coupling capacitors are Obbligato Gold Premium and Cornell Dubilier. There are only 3 capacitors in the signal path, but I'm going to remove the input capacitor because my line level signals have no DC component. We used existing component leads where possible and Teflon insulated hookup wire where required. The ground bus is 14 gauge bare solid copper wire. The wiring is almost complete in this photo. Still to come are the polypropylene bypass capacitors and the neon pilot lights. The big moment arrives. First time power up. No smoke, no flames. Voltages look good. All is well. Break out the champagne. The amp is up on blocks to keep it vertical while accommodating the meter leads that connect to the test points beneath the chassis. A decade resistance box indicates that I was tweaking something at the time. I think it was the B+ dropping resistor for the input stage. The 300B, 5U4, and most directly heated tubes are designed to operate base down or in a specified safe orientation. The filament expands when hot to the point where it can droop and touch other internal tube elements if the tube is not in a safe position. According to the tube manual, each of our directly heated tubes does have a safe horizontal orientation, but with our chassis layout, they are at odds. So to be safe, I keep the amps upright when powered up under test. AA334 final testing. Here our babies are up on blocks on the test bench. Each amplifier weighs 21 pounds. I burned them in over a period of a week or so. The voltages remained stable during that time, and the amps ran nice and cool. The power transformers only became warm to the touch after several hours. Here is the frequency response curve of one of the amplifiers measured at the 8-ohm speaker terminals. The response is ruler flat up to 25 kHz. The measured -3 dB points are 20 Hz and 40 kHz. Here you can see the frequency distribution of a 1 kHz sine wave at 1 watt into 8 ohms measured at the amplifier's output terminals. The spectrum analyzer's horizontal scale is 0 to 5 kHz and the vertical scale is 10 dB per division. Second order harmonics are more than 50 dB down, and odd order harmonics are not even visible on the display. This is good. Here are the AA334s on the burn-in bench. Our trusty VDAC plugged into the shop computer is providing music for our testing sessions. It sure beats listening to sine waves. This is a bottom view of one of the AA334s with the pilot lights and the bypass caps installed. One of my design criteria was to use only traditional methods and components, hence the neon pilot lights rather than LEDs. The orange pilot light indicates that power has been applied to the tube heaters, while the green pilot light indicates that high voltage B+ is present. Here are the finished AA334s happily powering our Klipsch Cornwall 2 speakers. Each speaker has a 15-inch woofer in a bass reflex enclosure, plus horn-loaded mid-range and tweeter drivers. Paul Klipsch named them Cornwalls because they are equally effective when placed in a corner or against the wall, so they're Cornwalls. Klipsch Cornwall speakers were introduced more than 50 years ago and are still in production. Their high sensitivity of 101 dB at 1 watt per meter makes them a good match for low-powered single-ended Class A tube amplifiers like the AA334s. This was a great project. It was fun, I learned a lot, and the amplifiers exceed my expectations. They certainly measure well. So how do they sound? Well, there might be some substance to this DHT-SET thing after all. I am impressed. In my listening tests so far, I could find no area where they are lacking. Bass is strong, tight, and musical. Vocals have clarity and presence. Instruments seem to have plenty of space around them. The AA334s have no problem driving the speakers to painful sound levels, and yet I heard no trace of clipping. The sound was never tiring even after hours of listening. The Cornwall 2s are 8-ohm speakers, so naturally I connected them to the amplifier's 8-ohm output terminals. Later, out of curiosity, I switched the speakers to the 4-ohm terminals and found I prefer the sound. Perhaps the bass has a touch more definition. Not sure. It's subtle. Here's the original AA334 schematic. After some testing in my audio system, I found that the gain was rather high. My signal sources are fairly high level. So what I did was I redesigned the input stage and installed a 6SN7 instead of the 6SL7. The L7s have a 70, an amplification factor of 70, while the SN7s have an amplification factor of 20. And this worked out much better given my high-level sources. I also have a passive preamp which has zero gain, essentially, and that works well. It drives the AA334s very satisfactorily. I'll end this video by giving a very quick demonstration of the AA334s installed in my audio system in my living room.